Hey everyone, welcome back to EP Edge. I'm Dr. Sharma, and this is the start of a 3-part EP Edge comprehensive analysis on pulsed field ablation, PFA. Let me frame what we're doing because this isn't going to be a here's the shiny new catheter episode. This is meant to be a grounded EP level review. History, mechanism, trials, and then complications. Here's the structure. Part 1, this episode, is foundational. We're going to build the mental model, what electroporation is, where it came from, and why PFA is not just as touted, RF without heat. We'll talk history, engineering, biology, tissue selectivity, and what lesions actually look like under the microscope. Part 2 will be clinical, pivotal, and most current trials of PFA in atrial fibrillation. Not just the top-line results. We'll talk design, endpoints, follow-up strategy, durability logic, and what success actually means when the mechanism is non-thermal. And part 3 is complications, the expected ones, the rare ones, and the emerging signals that remind us that selective doesn't mean risk-free. One more thing, the audience for EP Edge is broad. Electrophysiologists, fellows, allies, and industry. So I'll explain concepts just enough so everyone stays on the same page, and then I'll go deeper because the depth is where PFA starts to make sense. Okay, let's start where PFA actually starts, not in the EP lab, at the level of membrane physics. So electroporation. The simplest way to picture it is this. Cells have membranes, and that membrane behaves electrically like a capacitor. If you apply a strong enough electric field across it, even for a very short time, you can destabilize the lipid bilayer and create pores. Those pores change permeability. Ions move, water shifts, the cell's carefully maintained gradients start to collapse. But here's the key. Electroporation is not automatically lethal. If the field and the pulse parameters stay below a threshold, the pores reseal and the cell recovers. That's reversible electroporation. If the threshold is exceeded by amplitude, pulse width, pulse number, repetition, or geometry, repair fails. The membrane doesn't recover. The cell dies. That's irreversible electroporation. That reversible to irreversible concept, this threshold-governed continuum, is the core logic behind PFA. And it's also why PFA forces EP operators to unlearn a few thermal habits, because the causal chain is different. Thermal ablation is temperature first, heating, protein denaturation, coagulative necrosis. PFA is membrane first, electric field, transmembrane voltage, membrane destabilization, ionic catastrophe, regulated or non-regulated cell death. So when we say PFA is non-thermal, it's not just marketing language. It's a fundamentally different injury pathway. Now, where did this all come from? Electroporation wasn't invented for cardiology. Electroporation started as a biophysical phenomenon. Before it was medicine, it was industrial science. In food processing, pulsed electric fields were used for non-thermal pasteurization. Think milk, juices, where you want microbial inactivation without cooking the product. In biotech and genetic engineering, electroporation became the workhorse technique for getting DNA or other macromolecules into cells. You apply short, high-intensity pulses, the membrane becomes transiently permeable, and you get uptake. That era clarified two ideas that still matter for PFA today. First, electroporation is parameter dependent. Amplitude, pulse width, number of pulses, repetition rate, these define the biological outcome. Second, thresholds exist. Below a certain threshold, the membrane reseals. Above it, you transition toward irreversible injury. The term electroporation itself came from that biophysics world, the idea that electrical energy can cause pore formation in a membrane. So even before cardiology adopted it, the central principles were already established. Membrane targeting, threshold behavior, and the importance of electric field distribution over energy dose in the thermal sense. The translational turning point came next. in oncology. Oncology is where electroporation became an ablation strategy. First, there was electrochemotherapy, using pulses to enhance uptake of chemotherapeutic drugs into tumor cells. But then investigators pushed beyond the reversible range. They realized if you intentionally exceed the threshold, you can ablate tissue through irreversible membrane failure without relying on thermal injury. Irreversible electroporation, IRE, showed that you could kill cells while relatively preserving extracellular matrix architecture. And in some models, vessels and nerves were less injured than with thermal ablation. That concept is a big deal because it tells you the injury is not burn and scar in the classic RF way. It's a different biological injury with different healing behavior. Once that was established, the jump to cardiology was almost inevitable. Cardiac EP already relies on focal tissue destruction. The question was, can we do that destruction in a way that reduces collateral injury? And that brings us to the heart's own earlier history with electrical ablation. Let's zoom out for a second and talk about the ablation timeline in cardiology. Before catheters, there was surgical ablation. Then catheter-based strategies evolved in stages, each one solving one problem and creating another. One of the most fascinating moments in that story is how direct current ablation entered the picture. DC ablation was, in part, discovered through an accident. In the late 1970s, in a European EP lab, a patient with unstable ventricular tachycardia was undergoing catheter work. A catheter position inadvertently shifted, essentially to the His region, and a short circuit occurred with the defibrillator system. The outcome was complete heart block. That event was a proof of concept. Electrical energy delivered through a catheter could permanently modify conduction tissue. Over the next few years, that translated into deliberate DC ablation efforts, including early animal work, and then human procedures targeting AV conduction and accessory pathways. But DC ablation had major limitations. It was painful. High voltage meant arcing and explosive gas formation, and the shockwave effects weren't trivial. Ventricular arrhythmias, hypotension, even perforation. So RF took over. With RF, we gained controllability, thermal lesion creation with a more predictable workflow. Then cryo developed into its own niche, including balloon-based strategies for pulmonary veins. And now PFA arrives not as an entirely new idea, but as a controlled re-engineering of the electrical injury concept that DC ablation introduced, minus the chaos. That phrase, controlled re-engineering, is the right mental model, because modern PFA is not a shock. It's a finely engineered system. Here's the roadmap for part 1, this foundational episode. We're going to cover 4 pillars. 1, the Engineering Trinity, waveform, catheter, and pulse generator. PFA is a system, not a single energy source. 2, tissue injury mechanisms, how a membrane-first injury actually leads to cell death. 3, tissue selectivity, why myocardium can be preferentially injured and why that selectivity is conditional, not absolute. And 4, histology and pathohistology, what lesions look like acutely and chronically and why imaging can mislead. If you understand these 4 pillars, the clinical trials in part 2 and the complications in part 3 will make much more sense. So let's go into the engineering, because PFA is not just turn up voltage and hope. The waveform is the temporal control system. It's how we shape biology through time. Key parameters include pulse amplitude, pulse width, number of pulses, repetition frequency, polarity, and timing within bursts. Pulse amplitude is the dominant lever. Increase amplitude and you increase induced transmembrane voltage. You increase the probability of exceeding lethal thresholds, and you expand the spatial extent of irreversible injury. But amplitude is also where off-target effects rise. Field spill into adjacent tissues, blood pool exposure, and platform-specific risks like hemolysis or unintended neuromuscular capture. Pulse width is different. Think of it as membrane charging, not just duration. If a pulse is shorter than the membrane charging time constant, the transmembrane voltage may not fully develop. Very short pulses can favor electroporation with less electrochemistry, whereas longer pulses can increase electrode-tissue interface reactions and increase muscle stimulation and pain. Then pulse number and repetition, this is cumulative injury. But tissue isn't static during a pulse train. Conductivity can change dynamically as membranes become permeable. That shifts field distribution in real time. Finally, monophasic versus biphasic. Monophasic can be efficient for electroporation but tends to increase electrochemical and neuromuscular side effects. Biphasic can reduce electrode polarization and muscle capture but may change net electroporation efficiency. Bottom line, there is no universal PFA waveform. Every waveform is a trade-off: efficacy, selectivity, safety. Next is the catheter, because waveform is time, but catheter is space. If waveform defines time, the catheter defines space. The catheter is not a passive delivery tool. Electrode size, spacing, and configuration determine field intensity at tissue surfaces, penetration depth, and field uniformity. Small geometric changes can create large differences in peak, field intensity, steep gradients at lesion borders, and unexpected exposure in the blood pool. Modern PFA often uses multipolar designs, distributing energy over a larger area to reduce hotspots. But multipolar systems create complex superposition patterns that makes results geometry dependent. Positioning and anatomy matter. Now, contact. PFA is less contact dependent than RF because it doesn't rely on resistive heating at an electrode tissue interface, but it's not contact independent. Inadequate contact can still reduce coupling and affect lesion depth and field penetration. And there's an engineering reality people forget. Catheters and cables can distort fast pulses. The waveform at tissue may not perfectly match the generator output. That brings us to the pulse generator, the system stabilizer. The generator has to deliver high voltage, very high instantaneous current, fast rise times, and then do it repeatedly with consistent fidelity, while you're also trying to record microvolt level electrograms, and the load is not static. During electroporation, conductivity changes, impedance shifts, and the field redistributes. That makes feedback and dosing more complex than RF, which leads to one of the most important EP concepts in PFA, the acute silence trap, because reversible electroporation and stunning can suppress electrograms. Acute loss of signals or acute non-capture does not guarantee irreversible injury. Acute silence can reflect stunning, not durable ablation. That single concept, stunning versus death, will matter again in part 2 when we talk durability. Okay, engineering sets the conditions. Now biology decides what the tissue becomes. First, injury mechanisms. The governing variable is transmembrane voltage. The electric field induces a voltage across the membrane based on local field magnitude, cell geometry, and orientation. That's why generator voltage is not dose. Once transmembrane voltage exceeds a critical level, nanopores form. Pore formation is not a clean, deterministic hole punch. It's a phase transition with heterogeneity. Even within the same small region, some cells get sublethal pores, others accumulate lethal pore populations, especially near steep gradients. Then comes the continuum: reversible electroporation, stunning, delayed death, and irreversible electroporation. Reversible electroporation isn't passive. Cells must actively restore ionic gradients, calcium homeostasis, membrane structure, and ATP supply. If repair keeps up, the cell recovers. If repair fails, permeability persists, energetics collapse, and death pathways activate. Downstream mechanisms matter: calcium influx and overload, ATP depletion, mitochondrial failure, and oxidative stress, reactive oxygen species, and lipid peroxidation, which can deepen membrane failure and lock cells into irreversible injury. Now, tissue selectivity. This is the defining feature of PFA, but it's often oversimplified. PFA doesn't choose myocardium, it creates an electric field distribution. Injury occurs where the field exceeds the lethal threshold for that tissue under that waveform and pulse train. Thresholds differ by tissue type, and effective thresholds vary with waveform. In many electroporation frameworks used for cardiac applications, lethal thresholds are discussed roughly in the several hundred to around 1,000 volts per centimeter range, and myocardium often shows comparatively lower susceptibility thresholds than some adjacent structures. Why might myocardium be more vulnerable? Larger cell size and geometry can generate higher induced membrane voltage. Myocytes are also exquisitely dependent on membrane integrity for excitability, so even sublethal disruption can produce dramatic functional suppression. Esophageal sparing, one of the major clinical selling points, likely reflects a combination of higher effective threshold, distance-dependent field fall-off, and waveform choices that aim to maximize myocardial injury while limiting collateral exposure. Phrenic nerve data is nuanced. Some models show minimal impact, others show transient injury. Preservation of nerve architecture may allow recovery, but dose and proximity still matter. Vasculature and autonomic nerves can also appear relatively preserved within lesions in some histologic descriptions, which helps explain why PFA may reduce certain types of thermal collateral damage patterns. But here's the caution. Selectivity is conditional, not absolute. Selectivity breaks when non-target tissues enter the high field zone or when dosing parameters exceed thresholds for those tissues. Geometry, proximity, overdosing, and blood pool exposure all matter. And that sets up the emerging safety signals that we will address in Part 3. Silent cerebral ischemic lesions seen on imaging in some settings, hemolysis with possible acute renal implications, laryngeal or nearby nerve spasm phenomena, esophageal heating observations despite lack of classic fistula signals, phrenic effects, and rare arrhythmic events. Now, histology and pathohistology. What does the tissue actually look like? A recurring signature in PFA lesion descriptions is sharply demarcated injury because the field drops off steeply with distance. Acutely, you can see interstitial edema and sometimes hemorrhage, contraction bands, myofiber breakup, and cardiomyocyte swelling. It is not classic coagulative necrosis. A key concept is preservation of the extracellular matrix scaffold even as cardiomyocytes are eliminated. Over weeks, lesions remodel toward fibrocellular replacement, granulation tissue, fibroblasts, collagen deposition, without necessarily matching the thermal scar pattern we're used to. That creates an imaging pathology mismatch. Tools like late gadolinium enhancement were built around thermal injury assumptions. In PFA, acute imaging changes can look large, then evolve differently over time. So interpreting lesion size and durability by imaging alone can be tricky. Clinically, the implications are practical. Acute PV isolation may include a stunning component, EGM reduction is necessary but not sufficient, and acute silence can be misleading. So that's part 1 in a nutshell. History, Engineering Trinity, membrane-first biology, conditional selectivity, and distinct lesion pathology. In part 2, we'll take these principles and apply them to the clinical trials. We'll ask, how did they define success? How did they monitor recurrence? And what does durability mean when stunning and irreversible injury can coexist? And in part 3, we'll do complications, mechanisms, signals, and what to watch as adoption scales. As always, you can find details of trials, references, and graphs in an abridged form on LinkedIn and the full newsletter on my Substack page, epedge.substack.com. Thanks for listening. See you for part 2. This is Dr. Sharma, and bye for now.